Thanks for having me. This is going to be a bit of a departure because we're going to talk about glaciers. But the thesis of this talk is that there's something in it for people that care about tectonics, that glaciers are really well exposed. They move a lot faster, so you can see a lot more of the relevant cycle dynamics. And plus, ice shelves have something called rifts, or at least we call them rifts. I think there's a lot of interesting similarities and differences between tectonic rifts. And I guess I'll let you be the judge. I'll just dive right in here. This is a rift. It's about a couple hundred kilometers long. I think it got to be about 200 kilometers long before it finally broke off. It was incorrectly reported in the media as being the biggest iceberg that ever formed. It was actually the sixth largest. And to give you a sense of scale, this rift is about 100 meters wide there. We're flying, a couple hundred meters above the surface here with the British, or with NASA, with the Operation Ice Bridge. And that material that you see inside of the rift, that is what we call melange. It's bits of icebergs, basically, stuff that broke off when the fracture formed that's currently floating in seawater. So that also exerts an interesting stress on the rift walls. It's sort of analogous to sedimentation in a tectonic rift. Let's see, I'll just say a few terminology words that I'll use in and out. A crevasse is just a fracture that cuts part of the way through a glacier or an ice shelf. When it cuts all the way through, we start calling it a rift. Right, so the rift is filled with seawater and with icebergs that float inside of it. And crack is just another name for fracture. Rifts are fractures, crevasses are fractures. Okay, so when I say calving, then that is the mechanical separation of ice from a glacier or ice sheet. It's different than melting. It's the two ways that ice sheets, for example, in Antarctica lose mass is either through melting or through calving. All the melting in Antarctica happens in the water because the air is really cold. So it's all submarine melt. And then when I say ice shelf, what am I talking about? This is different than sea ice. So sea ice is ice that's formed from freezing seawater. It tends to be kind of 1 to 10 meters thick. Ice shelves are the part of the ice sheet that flows off into the ocean. They're really thick. So ice shelves can be as thick as a kilometer thick, and then they quickly spread out and they get to be a characteristic kind of 200, 300, 400 meters thick. So they're a lot thicker than sea ice. A big difference. Okay, ice shelf calving is a wonderful tectonic analogy. So some of the things I'll look into here are that we have many highly repeatable cycles of rift propagation. We have ice shelf rift dynamics that interact with what we can call the glacier stress field, or the glacier tectonic stress field, if we want to make an analogy. The ice shelves are much more, in a geological sense, better exposed. You can just see more of what's going on, I think, very easily. And there's interesting rheological analogies, including viscoelasticity, plasticity, nonlinear plasticity, temperature dependence. Okay, so looking at a case study here, we'll go to, this is the South Atlantic section of Antarctica, and we'll go to the Brunt ice shelf, which is sort of this 100-kilometer scale ice shelf that's riddled with these fractures that are shown on the right there in red. During our time period of study, we had GPS out on the surface that were placed there by the British Antarctic Survey. And the rifts that are shown here, we have Chasm 1, NR is the North Rift, HC is the Halloween crack. We call it the Halloween crack because it opened on Halloween Day. And we thought it might propagate into a base that was down there. So it's kind of spooky. So the Halloween crack name was appropriate. And the North Rift calved during our time period of study. So the North Rift broke off while we had GPS out there, which is kind of cool. Speaking to the highly repeatable, the kind of cyclic nature that we can observe here, the calving front before North Rift calved was almost identical to within some staggering amount of like map discretization error, was almost identical to the way that it looked when Ernest Shackleton went there in 1914 and 15, right before World War I. So, when they sailed a boat, had a steam engine that had been retrofitted onto it in 1914, and they mapped out the ice front, it looked almost exactly the way that it did just before the calving event. And we have all these historical, declassified spy satellites. And if you want to dive in, I realize you probably can't look in these pictures in detail, but they're all in high resolution in this manuscript that's in Reviewing the Cryosphere. ISAT-2 brings a wonderful new tool to study. It's new, it's a few years old, but really high resolution satellite altimetry. So this is just showing that we can get sort of kilometer spacing, but then along track, because the satellite altimetry gives us an along track product, we can get down to centimeter scale altimetric measurements that we end up averaging over about 10 meters. And that just gives us a wonderful record of the small scale dynamics of the rift growth. And what we see here that really surprised us and took kind of a lot of thinking to really get our heads around, we see this steady rift widening, right? Starting in 2017, then the ICESat-2 era in 2018 starts. This is a comparison, by the way, with also with imagery and the GNSS sites we have on the ice shelf. And then we see that the vertical dashed lines there in 2021, that's when calving began on North Rift, and when the iceberg finally broke off, the rift extension stopped. And so what exactly about the glacier stress field caused the rift widening to stop because an iceberg calved? This is really weird as a glaciologist. Usually we think about calving as potentially being this chain reaction thing, that calving should destabilize the glacier and favor faster deformation. So the fact that it stopped the rift widening was really perplexing to us. And we actually didn't even think it was real. We spent kind of over a year trying to figure out if this was actually a real signal. And it is. I can assure you that this is absolutely something that happened. And it turns out that looking at the tectonic stresses really elucidates what's going on. Before calving, we see that North Rift, which is just this little stub. I don't know if you can see my mouse there, but this little thing right here is the North Rift. And you can see that it's really nicely aligned. It's set up to propagate at about 45 degrees to the principal axes. So it's a shear fracture. And that is actually in itself an interesting thing glaciologically, because most glaciologists usually we don't model shear fracture actually in ice shelf. Ours is one of the first studies that really showed that shear stresses are really important for rift propagation. And then you see the rift here propagated, and then what happened is that after the rift propagated, the ice shelf relaxed into this state of stress that looks more like a freely floating iceberg. This whole area out here, you see is in biaxial extension, black arrows in both directions. That's basically more like an iceberg. If you're in biaxial extension, it means the iceberg isn't feeling the confinement from the surrounding glacier. And so basically what's going on is the reason why the rift, the place where we measured this is the rift down here, Halloween Crack, that we were measuring the extension on. The reason why calving slowed down the rift widening is because basically the stresses were relaxed. Because after calving, the stresses became more like that of a freely floating iceberg. It actually transitioned to this low stress regime that favored rift stability, which is kind of a new thing for glaciology. That's not a typical sequence of events that we usually think about. Okay, continuing on here. On the other side of Antarctica now we're on the part just underneath South America, but on the Pacific side. We're at Pine Island Glacier. This is one of the biggest single glaciers on Earth. It has just this enormous flux, and it's very quickly changing. The glacier actually looks nothing like this anymore. This event happened a few years ago, and the glacier subsequently has completely changed after a series of really large calving events. This is actually one of the last big calving events that happened there. Now they're all much smaller and more broken up. And what we just noticed we noticed a couple of funny things. You'll have to ask me sometime over drinks about the whole history of this data set, because it's pretty funny actually. But we have a fairly unique setup where we actually have a broadband seismic deployment on an ice shelf. That's not a super common thing to have. And we have this little finger of a rift here that formed, this branch, if you will, that formed while the seismometers were out. That's this thing right here. Right, so it's basically this thing. You see that it formed between these two times, T1 and T2, a few days apart. You see it in the satellite imagery. So we go to the seismic data to see what this looks like seismically, and sure enough, right there on May 9th, there's a big event. Okay, well, that seems like it's worth looking into in a little bit more detail. It's actually regionally recorded, so the times of equal travel time error that I'm showing here, that's based on regional estimates of the location of the event, which localize it right to where we think it started. And when we zoom in on the exact waveform, we see something that does not look like a normal earthquake waveform. First of all, we see this resonance that lasted for a few hours after the fracturing event. It actually goes on for about a day if you look all the way down to the kind of when it goes back to the noise level. So after this fracture propagated, the whole ice shelf resonated at its normal mode frequencies of about 90 seconds. And okay, that's cool, but we actually already had a theory for that, so it's not necessarily the most revolutionary thing ever. Like I think we may have anticipated that this happened. What we didn't anticipate happening is that if we zoom in even more to just to the higher frequencies and to just a few minute period right during the that peak of the wave energy, we see that there's this fascinating 300-second long waveform, which when I first I thought we plotted backwards because earthquake seismograms usually have the highest amplitude first, and then they decay in time with the coda. This is exactly backwards. It ramps up through time like a crescendo. And that happens over about a 300-second period that we interpret as the actual rift propagation time. We interpret that the whole rift is radiating energy. And so after it starts slipping, sort of in a crack-like propagation is what an earthquake rupture dynamics person would call it, that as the crack propagates, a greater area of the rift is deforming and radiating seismic energy. So you get this crescendo as the deforming area grows through time. We can measure it really precisely using just using satellite imagery. It's about 10.5 kilometers long, 300 seconds. That's a 35 meter per second propagation rate. And
Brad,
so,
Brad,
yeah.
you're at 10 minutes now.
Okay, how long am I supposed to go for?
Uh, you have like 3 minutes more.
Okay, thank you.
Thank you.
So, the two questions are why so fast and why so slow? First of all, you in linear elastic fraction mechanics, you expect things to accelerate up to the Rayleigh wave speed, or in opening mode, or in shearing mode, you expect it to accelerate up to the shearing wave speed and maybe hitting the super shear region between the PNS wave speed. So we're way below that, right? The Rayleigh wave speed in ice is about 1,800 meters per second. And yet, a lot of glaciologists would say that fracturing is this slow process that evolves over weeks. And so we're much faster than that. And this is just, I'll skip over this. This is just a few slides about how linear elastic fracture mechanics works, that stuff I just said. And so basically, what we think is going on is that the water flow into the rift is essential. And so I think there's an interesting tectonic analogy too here. It has to do with basin infill and how sedimentation slowly changes the state of stress within tectonic rifts. In our rift is filled with water, and if you sucked all the water out, the rift walls would close because the glacier is really carefully near hydrostatic stress balance, right? And so what happens is that if the rift opens too fast, it takes some lag time. There's some inertia in the system. It takes time for the water to flow in. And this actually creates surface waves and sloshing frequency. And so basically, we're able to model the slow 35 meter per second rift propagation speed with a simple ODE model. It's really cute. I'm quite proud of it. That basically models the flow of water into the rift. I don't think I have enough time to really go into a lot of this, but we've also done three-dimensional modeling of rifts. So the previous models I've shown are all highly simplified. And one of the cool things we get out of that again, I think has a good tectonic analogy, is that there's flexure that happens. That because there's this because 90% of the ice shelf is underneath water, 10% is on top, the part underneath the waterline experiences a depth-dependent pressure, but the part above doesn't. That creates a net torque that causes a top-out rotation of the ice shelf. And so that creates this sense of flexure. This is actually well known in glaciology at the ice front, but hasn't been described in terms of rift propagation before. Our three-dimensional study was the first study to actually look at this in the context of rifting. We did this for different geometries, for central rifts or marginal rifts, and calculated stress intensity factors using linear elastic fracture mechanics. Again, I don't think I have enough time to go into all of that in detail. We'll leave some time for questions, but I can point you all to these papers published over a few years. The things that we've looked at, the largest ever observed rift propagation event reveals hydrodynamic interactions with the oceans, most recently in AGU Advances. We have this paper in review in the cryosphere about glacier stress interactions and several papers about ice quakes. So again, I'll leave you with these thoughts that I think might be fun to discuss. Is there an interesting tectonic analogy? Could we all work together? I hope so. So I'm curious to hear your questions.
Awesome. Thanks a lot, Brad. That was awesome. I know this topic is is a little bit new to a lot of people in the rifting community. So I'm expecting questions. Of course, yeah, lots of hands. Sasha, you go first.
Thanks, Brad. This is a really fascinating topic, and you made a good case that there are some analogies to tectonic rifts. Could you also outline what does not work, so that we are not getting overly excited? For instance, I did not see any normal faults. Is it right, or did I just not see them?
Um, well, it's a good question if there's normal faults. Yeah, I don't think there are. Um, the seismicity, the reason I'm stopping to think is because we don't have, like, I think there's one study or two that have ever made moment tensors of the microseismicity on ice shelves, just because a lot of glacier seismology, you have this blessing and a curse. You can be very close to the source, you can be 100 meters away from your ice quake, but yet the challenge is that if you're more than a few ice thicknesses away, you get really intense dispersion because you have this really strong velocity gradient, right? You go from ice to water or ice to bedrock. And so if you're more than a few ice thicknesses away, the dispersion becomes insane. You don't get any body wave arrival, so you can't make moment tensors.
But do you structurally see any faults that dip at an angle that would indicate normal faulting?
I think so. There's a paper by Catherine Walker about these horsetail features that you find at rift tips sometimes. And so I think the answer is yes.
Okay, thank you.
Yeah, just morphological.
Valerie, do you want to go?
Yeah, I have a question regarding you showed a map you showed showing principal stress, and I was wondering how do you get those?
From a model.
Okay.
Yeah, these.
So
So we used this velocity field here on the left, and then we use what's called a shallow shelf approximation ice flow model, which has a lot of free parameters that we attempt to estimate, and then it predicts, I mean, you can get the strains directly from this. So you need to have some estimate of the rheology, and those are the free parameters that we tune in the model.
Okay.
So we come up with a model that can reproduce the velocity field, and then we just take gradients and use the effective viscosity to calculate the stress field.
Okay. So you assume viscosity and not plasticity, do you?
Yeah, that's right. Glaciologist, and I think there's a lot of room to talk about rheology. I'm not convinced this is the absolute optimal thing to do. But glaciologists use something called the Glenn flow law, which is simply a power law rheology. It's a power law in the effective stress that basically has some power law exponent, which is usually taken to be 3 for glacier ice, which is thought to reflect a certain type of lattice deformation in ice crystals. Whether or not that's the right thing to do for ice shelves, I think I would be happy to have a discussion about that. There's a lot of ongoing research about this.
Some great. I see another hand up. Reha, do you want to go?
Yeah, hi. Can you hear me?
Yeah.
Hi, Brad. I thought that was a fascinating talk. Thank you very much for it. I'm a quantitative geomorphologist, and I was wondering if these studies apply to ice sheet expanses located on bedrock, like on rock, not just floating in water. And if these studies can have any results like to be used to study like landscape evolution, dynamics, any geomorphic techniques can be applied to this, like glacial geomorphology can be applied for this, or any implications for landscape evolution as well.
Yeah, absolutely. So let's see. I'm just going to do something really risky here. I don't know if this is going to work. I'll share just a paper. Here, watch this. Yeah, so we wrote this paper about, geared towards sediment entrainment, thinking about landscape evolution and looking how glacier seismicity on land is related to sediment entrainment. And basically, what we came up with, so here we have this table. We looked at all different studies that did experiments on ice and rock at different temperatures and different regimes. And we basically decided that the only way that we could explain glacier seismicity at the bed of grounded ice sheets or glaciers was that it basically has to be rock on rock friction. That ice on rock friction and ice on ice friction is simply never velocity weakening. It's never capable of producing ice quakes. And so all of this chatter that we see under the glacier, we think it's actually rocks banging against each other. And it turns out this is really consistent with this idea of a frozen fringe, which if you've done any groundwater hydrology, that language is an analogy to the capillary fringe that happens at the edge of the vadose zone. So basically the idea is that there's some fringing region where the ice penetrates down into the bedrock and is able to pick up and carry rocks away as it travels. So yeah, we've worked on kind of using that to understand landscape evolution processes.